Okay, good morning, everyone. Probably let's wait for 2 more minutes so that more people will come in, hopefully. Okay, I'll just start. Good morning, everyone. Hope you all have been well. Welcome back to ELEC3204. Let's have a recap before carry on to new content. So last time we talked about some materials you can read from um, book chapters. Um, so you can get them from the library. Um, but I want to emphasize again, everything we want you to learn, everything you need to know are in the lecture notes. So don't let it leave your hand. And the course structure, we also talk about course structure and some tips on how to do the course well. We talked about the history of wireless communication systems. Um, we especially um, discussed the concept of OFDM. Sorry, not this one here. So we especially discussed about the concept of OFDM, which helps to mitigate an effect called multi-pass effect. It happens when, for example, you are in a room, there is a transmitter and there is a receiver. So when the signal is transmitted, it gets a lot of reflections, right? Uh, there is there's normally a direct link as well, which is called line of sight, and there are a lot of reflections. And all these signals arrive at the receiver with different delay and different signal power, and they added together, sometimes constructively and sometimes destructively. So when signal power is bigger than channel power, then the signal cannot go through the channel without any harm. There will be interference. So OFDM helps to divide the signal power to multiple parallel subchannels, so that for each subchannel, the fading is flat, which means the signal can go through the channel um, without having any harm, without having any interference. So this interference is called inter-symbol interference. Um, we also talked about multiple input, multiple output technique, which is when you use multiple antennas to do signal processing. We'll be working on this for your coursework. I'll put up your coursework content probably next week. We also talked about the future of wireless communication systems. I hoped that you understand that. So basically, satellite communications, aeronautical communications, they essentially follow the same principle as terrestrial communications. Um, so we will revisit something like this today when we study the concept of channel modeling, so they kind of follow the same phenomenon, but because they have different characteristics, so they do have differences. For example, satellites that are very far away from the ground, so signal transmission from satellite to the ground would suffer more delay. And airplanes, they have higher mobility, so the communication here will suffer more from Doppler effect. We also mentioned Doppler effect many times. Doppler effects happens where the signal wavelength changes when either the transmitter or the receiver experience high mobility. So either the transmitter or the receiver is moving. That would cause a change in signal wavelengths. And when signal wavelength changes, the nature of the signal characteristic would change. We will revisit all of this many times, so you probably will notice that I will repeat many concepts many times throughout my sessions in the hope that it would enforce your impression on these concepts. Although probably at the first time, it wouldn't make a lot of sense. I hope that after I enforce this concept to you many times, you will be able to be brainwashed to remember them. So these are some concepts we are going to cover in the following sessions. And the first technique we learned from this course was called multiple access techniques. The first one is the first option is FDMA, which is when different users are differentiated in frequency domain. So different users, they use the different spectrum resource. They can't hear each other. They don't interfere with each other. And then TDMA is the second option, where the different users are scheduled to communicate at different times. So they do not communicate all at the same time. They don't conflict. So there is no interference with each other as well. The third option is CDMA. So it's like different people are communicating at the same time using the same channel, but they are speaking different languages. So their messages are encoded in code word design. They are all assigned with their own signature. So understand signature as a language that only a transmitter and a receiver understands. Only a pair understand, so that different pairs, they can use the same resource at the same time without interfering with each other. So the second part of the course will be covered by Liang Yang, and he will be teaching more about CDMA. The fourth option is SDMA. Excuse me, sorry. So the fourth option is SDMA. So for SDMA, different users, they use the same channel, they communicate at the same time, and they probably use the same code as well, but they transmit. So this is user 1, user 2, user 3. They transmit signals to base station from different directions. So if the base station knows that the signals, they come from different directions, the base station can still differentiate different users. There are two concepts you want to remember from these slides. First one is the cell structure. So normally we draw a cell like this. There is normally a base station in the middle that would provide coverage to this cell. So any user in this cell will be served by the base station in the middle of the cell. So first concept, cell either coverage or cell structure. Second thing from these slides is frequency reuse. So the spectrum resource is limited natural resource. So in reality, we always have to reuse them. So each cell is assigned with a frequency band. So the cells associated with the same number, for example, the cells associated with number 1, they all use the same frequency band. And for number 2, they are all dark colored cells. So you can see that the arrangement of cells is to make sure that the cells with the same frequency band, they are separated as far as possible, so that we have as small as possible for interference, but we are still able to reuse the spectrum resources like periodically. And then from this figure, you need to understand the concept that you need to have a general understanding that the cell size or the coverage can be different depending on where the base station is, and also depending on the power of base station. So a base station deployed high up at a building top can see a lot of things on the ground, can see a large area. So it provides a large coverage, which is called a macro cell. However, in cities, in urban area, there are a lot of buildings, there are a lot of cars, people moving around. So there will be a lot of blockage. When you have a base station here, the signal can be blocked by a building in a city environment. So sometimes we have to deploy base stations more frequently in an urban environment. So that would provide a microcell, which is a smaller coverage. And then indoor environment is very hostile because in indoor environment we have walls, we have many objects in the indoor in the room. So when you actually transmit a signal, the signal will have a lot of reflections in the room. So so normally, in order to provide a better coverage for indoor environment, we sometimes put base stations in indoor as well, which is sometimes also called access point. So this access point would provide even smaller coverage called picocell. So that's all from last time. This time we'll be talking about channel modeling. So you have all heard of an organization called IEEE. We have in Highfield campus, we have a building named after IEEE. So IEEE is the biggest organization for electronic engineering, and it has a lot of professional societies. So each society, they have their own science conferences and science journal papers. So the societies that are related to wireless communications are Information Theory Society, Communication Society, Signal Processing Society, and Vehicular Technology Society. So normally people people in our field normally regard Information Theory Society as the most prestigious society. So their conferences and their journals are very difficult for researchers to have a paper to publish in their society. A lot of issues of channel modeling is dealt with by Information Theory Society. That is how fundamental and important channel modeling is. So in the following few sessions, we'll be learning channel modeling. This is a very important area. So I hope we build up the foundation very solidly, so that we so after channel modeling, we will be able to learn signal processing technology better. So yeah, here, so we did talk about a little bit about signal bandwidth and channel bandwidth. So there are two definitions of bandwidth here, which can be confusing. So the first one, I often call it signal bandwidth, but strictly speaking, it should be called system bandwidth. So in exams, you always write down system bandwidth, but you can think it's signal bandwidth. Why? Because signals are generated by artificial systems, right? So so we can think of a signal bandwidth, but strictly speaking, it's system bandwidth. The second bandwidth that I talked about was channel bandwidth, but strictly speaking, the full name is the coherent bandwidth of the wireless channel. So so in exams, you should use the full name, but it helped me to understand that when signal bandwidth is smaller than channel bandwidth, the signal can go through the channel without any harm, without any interference. That scenario is the benign scenario. It is a good scenario. So it is called a narrowband system. So strictly speaking, it happens when system bandwidth is less than the coherent bandwidth of the wireless channels. It is also so this type of fading is also called frequency non-selective fading or flat fading. So coherent bandwidth here defines a collection of frequencies over which the fading channel is considered flat or constant, or it doesn't change over these frequency bands. So you can understand, just think it's channel bandwidth. But the definition is the coherent bandwidth of the wireless channel. We will revisit the concept of coherent bandwidth in later part of the course. But yes, William.
I was just wondering how a wireless channel can have a bandwidth, if that makes sense.
Yeah, that makes sense. Yes, thank you. So let me try to explain. Because we are going to revisit the same concept many times, so maybe it will help you to understand later on. But right now, let me try to explain that. So what is channel? There is a transmitter, right? There is a receiver. So when you actually transmit signals, it goes everywhere, right? It doesn't just directly go to the destination or the receiver, right? But if you are in a room, you have many reflections. You have millions of reflections, actually. But from the receiver's point of view, you only received substantial power from a few reflections and from a few links. So from the receiver's point of view, if you receive a Y, and then if what you transmitted was X, from the receiver's point of view, you receive a lot of replicas, and then there will also be noise. So there are a lot of signals, but from the receiver's point of view, you have this as the channel that you care about. So this is the channel. So your question is, how can channel have a bandwidth? So the definition of coherent bandwidth is defined as a collection of we have learned in here signal transmit over a frequency band. So coherent bandwidth defines a frequency band over which the fading is considered constant. It doesn't change. So that collection of frequencies is considered channel bandwidth. So you remember I draw it here equals h x and noise. So channel's bandwidth is the collection of frequencies or frequency band over which h does not change. It remains constant. If h is changing, then we would have problems. I'm not sure if that answers your question.
Yes, it does. Thanks.
Okay, good, very good. So basically, let's think if the signal bandwidth is become bigger than the channel bandwidth, then the signal cannot go through the channel without any harm. That system is defined. It's called a wideband system, and the fading of that type is called frequency selective fading. That's where OFDM starts to help, because OFDM would divide the signal bandwidth to parallel smaller sub-channels, so that each sub-channel of signal can go through the channel bandwidth without any harm. So for each sub-channel, it is frequency non-selective or flat. We'll revisit all these concepts many times throughout the course, but do raise your hand if you need a bit more explanation when I mention these concepts. So things can get worse. So if the signal bandwidth is even wider, the system become broadband. The definition of broadband is different from computer science. In computer science, when you see the word broadband, you probably think about internet connectivity. But here it labels, it defines the system that the signal bandwidth is really wide. And then things can get even worse, which is ultra wide bandwidth system. Actually, in modern communication systems, we normally only have these two. So we often encounter these two more often, narrowband and wideband, because we have a lot of channel bandwidth to use now. We have a lot of spectrum resource for 4G, for 5G. We have more spectrum resource than before. So normally the channel bandwidth is higher than, say, 20 or 30 years ago, when broadband system and ultra-wide bandwidth system was defined. However, it's important to understand the classification of different systems and understand why they happen. So basically, two concepts of bandwidth here: signal bandwidth and channel bandwidth. And the threshold is over here. So narrowband system is benign, it's a good scenario where there's no interference. So we have enough bandwidth for signal. And then when the signal bandwidth is bigger than channel bandwidth, we need OFDM to help. Yes? Did someone ask a question? Right, I'll just move on for now, if that's okay. Hold on. I can't find the current page on my computer. Right. Yeah, here. So in terms of channel modeling, so this classification is very important. Take a mental image of this slide. We'll be talking about this again in the afternoon. So there are three types. Normally there are three types of channel modeling. The first is path loss. Last time I also mentioned that when signal propagate over distance, the signal power would reduce over distance. That is called path loss. So signal power would decrease over distance. Shadowing happens when, for example, in an urban area, you have buildings that cause blockage, or in rural area, you have mountains that cause blockage. So that kind of blockage would cause a sudden decrease in signal power. So that is, so this channel model is called shadowing. This is also called shadowing effect. So which is a sudden blockage on signal power. It is also sometimes called slow fading, because when you have a building there, it doesn't move. The environment doesn't change just rapidly. So it's also called slow fading, because this type of fading doesn't change when you have a blockage. The blockage can last for a really long time. Okay, and then fast fading. Sometimes many people also call it small scale fading. So it happens when, for example, you have a transmitter, you have a receiver. Either the transmitter or the receiver is moving, or when you have signal transmission and you have reflections, right? And some of the objects that reflect your signal would probably be a moving car. Then the signal characteristic would change faster. So that would cause power fluctuation, dynamic power fluctuation as a receiver. So this is also called fast fading or small scale fading. There are more to this, all of these concepts. I will keep repeating these concepts and adding more details to them as we go. But take a mental image of these slides. Remember that path loss is gradual power loss over distance, and slow fading or shadowing is a sudden blockage of power loss. And then fast fading is like a real time and random power change as a receiver. Right. So there are different effects, different factors that affects wireless signal transmission. So we did talk about path loss, which is signal power decreases way over distance. And then reflection is also quite simple. It happens when signal reflect on a surface. So normally, when reflection happens, the direction of signal would obviously bend, and also um, it will the signal travels through a reflected path here. This path is longer than direct path. So traveling over the reflected path would take more time, so it will cause a delay, and also it will cause a phase change. This is important because at the receiver, different paths, they will added together. So this effect is also called multi-path effect. So all of these replicas of signal, they will arrive with different delays and different phase rotations and different powers. So that is very harmful for wireless communications. Diffraction. You probably remember for A level, you have learned that for visible light, when it passes through a slit, like the signal kind of bend. So it's probably a terrible draw, but anyway, when a signal passes through a slit, it kind of bend. That happens in visible light. So last time we talked about the spectrum of wireless communication, which is between the spectrum of voice and spectrum of visible light. So for radio frequency spectrum, we use this spectrum between voice signal and visible light signal, so that we use this spectrum for signal transmission and reception, so that all of these wireless communication systems, they don't interfere with our everyday life. We don't see them, we don't hear them, but they are there to forward the signals that we need. So all of these signals, they have lower frequency or equivalently higher wavelengths than visible light. So the bending here would happen more often in radio frequency in wireless communications. For example, you all have a Wi-Fi router at home, or we call it access point. So there are antennas on your Wi-Fi router that provide coverage for your Wi-Fi access. You don't have to be in the same room as your Wi-Fi router, right? But you don't when you are not in the same room as your Wi-Fi router, there is no direct link between you and your Wi-Fi access point. But you can still receive good coverage because signal kind of bend when it passes through like edge of the wall. So it kind of it feels a little bit like magic, but it actually works in our favor because we don't always have to have a line of sight to the transmitter, to the transmitting antenna to get signal. And then scattering effect happens when signal impinge on a rough surface and then you get a lot of scattered signals out of the surface. So a lot of copies going off of the surface. All of these three effects lead to dispersion, which is really harmful because once again, you have a lot of replicas of signal arriving at the destination with different delays and different signal powers. In visible light, it is like your vision is become quite kind of blur because you have replica of the same signal, and they kind of interfere with each other. They arrive at your eye with different delays and different phase rotations, different powers. It happens less often in visible light because what you normally see in visible light are line of sight. So you have to be able to see them. They have to have a direct line of sight so that your eyes can see them. But in wireless communications, even when there is no line of sight, we still need those signals. So the dispersion is more severe in radio frequency in wireless communications. Doppler effect, we talked about it before, so I'm going to skip it for now. So we are going to learn three types of propagation path laws. So for the first type of channel modeling path laws, we're going to learn three types of path laws. I'm a little bit under the pressure of time, so I'm going to stop taking questions from here. But do send me an email afterwards, and we can discuss more in the afternoon. So the first model is free space propagation path laws. Free space propagation path laws. It happens more often when there is a line of sight between the transmitter and the receiver. So it happens actually more often for satellite communications. So when there are two satellites in the space, there is nothing in the space that would reflect your signal. So there is a clear line of sight. So the power change can be perfectly modeled by free space propagation. However, having said that, for terrestrial communication, so for normal wireless communication on the ground, we also often use free space propagation path laws as a reference to calculate how much transmit power we need and how much receive power we'll get. This is related to coverage calculation. So the free space path laws is defined by this equation. We will look at this equation from different angles in the following slides. So this equation is really important. You are expected to be able to understand all the parameters of this equation and derive further from this equation to its different forms. So PR is the received signal power. PT is the transmit signal power. GT is the antenna gain of the transmitter. GR is the antenna gain as a receiver. So antenna gains, they are fixed once your antenna is manufactured. So it comes with your product specification. When you have a mobile phone, it's already manufactured, so it always has a fixed value for antenna gain. And the lambda is wavelength, which is calculated by C divided by F. So c is the speed of light. F is the center frequency of a frequency band, the frequency band you are using for signal transmission. So lambda is wavelength. And d is the distance between the transmitter and the receiver. So we can see here that the transmitted power, so with a fixed transmitted power, the received signal power is a function of distance. So as the distance increases, the received signal power would decrease. So let's look at an example. So don't worry if there are too many concepts in here. I will explain a few examples. I do raise your hands here if you find it difficult to understand. I will note and I will come back to these slides in the afternoon. So yeah, don't worry that if there are too many concepts on this slide. So this is not exam material, but it will help you a lot in understanding path laws. So we have all heard of the terminology called millimeter wave, which is used in 5G. So it is called millimeter wave because its wavelength is on the magnitude of millimeter, right? So different frequency bands, they use a different range of frequencies, and we can calculate wavelength by the equation that wavelength equals to speed of light divided by central frequency of the frequency band. Okay, so if we only consider this part first of the path laws equation, then we can look at example 1. We only consider the part that concerns distance, and we evaluate it in log domain, so it is in decibel. So we can see that if we fix the path laws, so say we have a power, and then we say for this system, we can only experience a fixed path loss. So if the signal is faded a little bit further, then the receiver cannot detect it. So with a fixed path loss, using this equation, we can calculate the distance that is allowed for signal to travel. That distance is also called coverage. So because the equation is a function of distance and wavelength, we can see from example 1 that for millimeter wave, the coverage is smaller than before. So that's why we often say that millimeter wave has smaller coverage. So we need to deploy more base stations to provide seamless wireless coverage. But that's not the end of story yet. The second example, I'm not sure if you remember, we talked about why millimeter wave hasn't been used widely in wireless communication before 5G. So it is related to related to the area of antenna. So last time I said that as the frequency increases, the size of antenna would decrease, right? So when you look at the word aperture, just think it means the area of antenna. So it follows this equation. The area equals to this one. So G here is the antenna gain. We saw antenna gain in path loss equation. So antenna gain here. is related to antenna area. Okay, so this equation is also related to wavelengths. So based on this equation, as wavelengths decreases in millimeter wave, the antenna gain would actually increase. So this works in our favor. So conventionally, without considering antenna gain, the coverage would decrease. But now we consider antenna gain, we have more signal power, so it can compensate for that path loss and provide ideally the same coverage as before. So that's why I said for millimeter wave, the coverage is actually, or the signal power is not necessarily lower than before, lower than LTE, lower than legacy systems. However, I also said that in millimeter wave, one of the reasons why millimeter wave wasn't widely used in wireless communication before was that it was difficult to manufacture. So we can see in equation 3, so if we define a fixed antenna gain, so we say we need this much of antenna gain for signal to successfully get to the receiver. Then based on the same equation here, as the wavelength decreases in millimeter wave, the antenna aperture decreases. That's why we often say that the antenna size is smaller when the frequency increases. So you can see quite clearly here that the antenna size is shrinking, or the aperture is shrinking. The last example is called angular resolution. So it follows this equation. So if I fix the antenna aperture, so when we manufacture an antenna and say we just need this fixed area of antenna, then as the wavelength decreases in millimeter wave, the angular resolution would decrease. This is angular resolution, which also means that the manufacture of antenna in millimeter wave is more difficult. So these three frequency bands, excuse me, are all between the frequency band of voice signal and frequency band of visible light. So we are using a frequency band below millimeter wave before. We are starting to use millimeter wave. We will probably start to use terahertz for 6G. But the reason we are slowly using higher frequency band now is that at higher frequency band, we will have higher path loss, so smaller coverage. In order to compensate for it, we need more antenna gain. But in order to get enough antenna gain, the antenna size becomes smaller, and also the angular resolution becomes smaller. So it's more difficult to manufacture. You don't have to remember all the details of this page, but it would be helpful if you followed the rationale that I just explained. So do let me know if that's not clear. I will explain it again in the afternoon. So parameters of equation 1. So equation 1 is this. So parameters out here, I have explained every one of them. So PR is the received signal power. PT is the transmit signal power. GT, GR are antenna gains. And lambda is wavelength. F is frequency. And then we often need to. I was going to ask you a question here, but we don't really have time. I will try to finish in 5 minutes. Sorry, this session lasts a little bit longer now. So we normally need to calculate to do calculation in decibel. So my question was, I was going to ask you, why do you think we need to calculate everything we want to calculate everything in decibel? It's just not, it's not just because of convenience. It's because when we calculate the equation of path laws, all the relationships are, there are multiplications, there are divisions here. They all become additions and subtractions in log domain, right? So in this way, we can analyze each element separately. We can analyze them independently. We have already done that in the examples I showed you before this slide. So we look at distance independent of the frequency. When we need to see what's happening in millimeter wave, we only consider frequency. And when we look at the coverage, we only look at the distance. So calculating this in log domain would help us to look at these parameters separately. So one takeaway from this equation is that whenever you have 10 more meters of separation between transmitter and receiver, so if you travel 10 more meters, you get 20 more dB in signal power decay. So signal power would decrease for 20 more dB when you travel 10 more meters. And then this equation is an alternative. This is exactly the same as before, only that the metric here become kilometers, and the metric for frequency is megahertz. So when you actually input values to equations, sometimes for the sake of convenience, you only want to input values on the magnitude of kilometers or on the magnitude of megahertz. So this is actually for the sake of convenience. I don't want to talk things too fast that it would be really hard for you to process. So I will stop here, but it's really important. The important message for free space propagation is that from equation one is really important. You need to understand all the meaning of all the parameters. And from equation 1, we derived equation 2. The reason is we want to evaluate the path loss in decibel so that we can look at each parameters separately. And then alternatively, we have equation 5 and 6, which are in different magnitude, but equivalent to what we have before. So all these 6 equations, this is a good example that if you are given a piece of paper, you should be able to write down equation 1 all the way from equation 1 to equation 6, and you should be able to explain the motivation behind the derivation from equation 1 to equation 6. So why we move from step 1 to step 2, step 3, and eventually we arrive at equation 6. So explain a little bit more, and I will elaborate on this a little bit more in the afternoon. So that's all for the morning session. For now, see you all again in the afternoon.